this is working. And welcome to the talk. And I'm very glad and thankful that you are here for my introduction to this technique, to the 3D X-ray microscope. And now standing here, it's really a difficult task because actually I have to give 2 talks to present you the device, the X-ray microscope itself, and then to tell something about digital image analysis, because that's what our results are. When we do measurements with a 3D X-ray microscope, we measure a 3-dimensional image, and then we're going to investigate this image. And this is what I'm going to tell you about. So we introduce the method, we get to know maybe suitable samples, and get something to know about image volumes. Myself, if you want to contact me, I'm the lab manager of this Xray Microscopy lab. I'm sitting in the Geo building, and I'm sure we can exchange later my contact address in case you don't have it. Also, if I'm going to talk too fast for you, I have set up a website. That's what we have here. So it shows you for the whole 3D material analytics area some information stored here, what I'm telling about. And we have a bunch of devices in this area that actually investigate 3D materials. And today, this is our instrument we're going to have a special look at, the Zeiss X-Radia 520 Versa. That's the 3D X-ray microscope. And I'm going to tell you about this device. It has X-ray source, a lot of detectors, and it produces volume data sets that we can then investigate with our digital image analysis. So today's topics, we get to know some fundamentals of this technique, including sample mounting and preparation. Maybe we'll look into the lab how this works, and we get an idea of the field of view, and in the same size, the voxel size, how good is the resolution of my 3D image? And what is quantitative digital image analysis all about? Of course, we do that on the fly by some examples I hope to present you. Let's start. If you think of X-ray imaging, you get different kinds of images. You see sometimes here something with a light background and dark features here. That's really the transmission image when you put the different samples in the beam and you let the detector take an image. So the incident material in the beam absorbs X-rays, and where it's dark, it has a high X-ray absorption. The structure absorbs very much X-rays. And where it's light, not so much. The material is not so dense. So we get an idea about the density, and the density contrasts by these transmission images that then later will be reconstructed to 3-dimensional volume images of the X-ray absorption. And if you look at that, we have many images on that side that have a dark background, and we have features that are very dark and very light. And now in this case, if we reconstruct the X-ray absorptions, the areas where we have a lot of X-ray absorption, these are reconstructed in light colors, and if we have a low density, low X-ray absorption, these are the dark colors. So we see some porosity here. And sometimes we see, that's a nice thing, a corn sprout in a sand environment. And also often is involved that we have 3-dimensional models, like they are counted nice, colored nicely. And this is going to happen then we look at with digital image analysis. We have these different gray values, and if we have here this kind of titanium oxide powder, and we are interested what's the shape of these, we're going to get all the voxels here that are light, make a 3D model, and then we can maybe look at the surface or the volume properties of these different things. So we can have a lot of images here, and some are just straightforward, give us an idea of the strength of the X-ray absorption, and others we can perform turn them into a 3D model, and then we can measure the surface and the volume properties. So that we have these kind of different images has to do with the imaging workflow. So first of all, of course, we do a scan, and then we have a computer that reconstructs this information that we get from the scan. During the scan, we have a sample rotating a full 360 degrees, and we see we have different structures here, different maybe minerals, we have a pore space, and if we look closely, we see something is turning around. We see the object from every side. The computer takes this information and reconstructs a three-dimensional object. And then it produces slice-wise a stack of images that has now the X-ray absorption color-coded from dark to light. And we see this is something, this kind of data volume. It can be between 4 gigabyte and 16 gigabyte or something like that. This is what you will get when you are a costumer. You give your sample, we measure it, I reconstruct the density, and then later what you get is this stack of images which then you can process at home. Or, of course, we make a cooperation, and I can give you a short guidance or support you in using the correct software. Because once we have that stack of images, now the interesting thing starts when we see, we just look after it is reconstructed. When we look into it with a digital image analysis, we can look at the different layers here. We see different materials like air, like iron sulfide, very absorptive, or we have here volcanic glass or something like that. It would be interesting to know maybe some volume percentage of this kind of filling in this kind of void. And what we do then is that we do something that we call segmentation. We take all these iron sulfide voxels into one 3D model, and then we calculate, for example, the area percent, or in 3D, the volume percent of that kind of filling of iron sulfide in the void, that, so we can have a volume percentage. Or we could use porosity, something like that. So we can really quantify something of these kind of 3D models from our technique. And scanning is normally done in a day or in some hours. Reconstruction, nowadays it's about 10 minutes or even less. And the work with this kind of information, with the digital image analysis, could be from days to weeks, depending on the depth you want to go inside with your data. So let's see if we get this kind of image volume data set. What is it actually? So if we have this kind of sample here, it's a medicine bottle from a ship's pharmacy from the German Maritime Museum. It's an artifact in a museum. You cannot open it. So if you want to see what's inside, a good thing is to do a scanning. What we do then, we take 1,000 to 3,000 images in several rotation steps, and we see this image has a kind of perspective. We have a point-focused X-ray source here, then you got a beam, and you got on the other side you got a detector, and this kind of sample is just bathing in the X-rays. And it has a kind of cone beam, it has a kind of perspective here, because in this direction you have a magnification, and sometimes you see that you have a kind of perspective here. This palette here now is smaller than the other, but when we turn it, it appears, and it's correct that, now you see the other side, this palette now is bigger. So we really have a perspective in these kind of scanning images, and the computer then is trying to reconstruct this model. So the computer thinks, what's happening with the sample, how does it look like from all sides, and then present you a volume data set. And what we do now basically with our data analysis is that we inspect these kind of volume data sets with some software. What is a volume data set? You can perform some kind of virtual thin sectioning. Then you can open it. You look inside, you see this kind of pills. There are some organic material, of course, had to be eaten by the sailors, maybe against seasickness or so. And this kind is presented here in a glass bottle. You see, if we take a look at that slice that we just took away, a virtual thin section, we really see different materials because we have different gray values representing different strengths of X-ray absorption. So we have here a glass, a silica glass, and here this is very light. So we have a lead glass that's heavier, of course, has a stronger absorption. So nicely we can see different materials here, or the air, or these pills. We see that they were, in the old days, they were really milled and put together. Like we can see, look into processes. So here we can really look into processes. Did the guys mill it a bit before they put these together, or is it just a bit coarse? Handmade pills for the sailors, and this is something that gives us information also about processes. How were these pills produced? Then we see we have this detector that has some kind of voxels. In our device, it's 2,000 times 2,000 voxels, for example, and so we have an image. Each image that is taken has a certain number of voxels, and that is the nature of our data. That also, if you look more closely, sets the limits of our resolution. So if we, in this case, we have a voxel size of 97 micron. And if we want to look more closely, we have to make a high resolution image to see not the whole sample, but maybe only a portion of it. And this is also what we can do. So what we have this image volume. We can see different slices in any orientation, and each slice represents an image. It's a layer, and this layer, each image has a thickness. It really has a thickness depending on this geometric position and relation of this kind of detector pixels, how big are they really, and this kind of distance here with the magnification effect, so that we have here a kind of, really a measurement. The thickness of a layer we can measure as distance. And that's how we get. So when we have our digital image volumes, I here can present a drill core. Then if we scan it, it looks like this. Some dark minerals, very heavy in X-ray absorption. And now we have different representations of this volume image data set. We can perform a volume reconstruction. It's a visualization of this data set. So we see density contrasts. Everything that is light here is a heavy mineral. It absorbs a lot of X-rays, and other silicates here are less dense or contain different minerals. And we can see now, because of these density contrasts, we see different rock compounds in our working piece here because of the density contrast. So this is the kind of volume reconstruction with classical shadow-based. We can see like as if it's a 3D object. We can also perform virtual thin sections here. And then I can start, because we see this is a kind of, these things are very bladed minerals here. And so if I pick several of them and make a 3D model of those, we see they have orientation. And this is something also for you. If you have a process that inflicts orientation of material, you could just analyze it, and then maybe seeing, for example, these ore things that we see here. Also the ore minerals have orientation. And later you can see, if you take this cone in the field or in your working bench, what is the kind of orientation, the process you're working on with your piece opposes to these minerals here. And so what I can do, if I have the 3D models of all the minerals, I can see what's their volume, how is the volume percentage of this ore and this rock, what's the surface. Maybe if I have a reaction to observe, reaction rate, it depends on the surface. I could look at the surfaces or the thickness of the minerals, how long does it maybe take to grow in a process, or the orientation. Really nice things you can all measure from segmentation of certain phases, fabric components in your sample. For example, in terms of this orientation, I could do these kind of things here and relocate it in the field. If we have a something in the geological field during the formation of the Alps or something, I can see if there has been a pressure system and to which maybe the growth of this mineral responds, and I can really perform some orientation maps, like here. Normally I thought, oh, you're coming from the different IFAM or something institutes or fiber institutes or IWT or the Hochschule Bremen and the ZMT. So I could just take one of your scans. But then I thought, oh, I'm not sure if this person's ready with their work, or maybe the paper is not published. So instead of talking about something that you all did, I continue with what I did to describe what you can do with the data set. So it might be a bit sometimes geologic, but of course you have to think of that, relate that to your own stuff. So what can I do when I have these volume data sets? For example, if I have this submarine volcanic rock, we have endolithic life in these kind of things. We have fungi, we have bacterial mats, and the question is, and from the Greenland Sea here, in these voids we have fungi and we have bacterial mats. So how do the life enters the rock? That was one of our questions. And so we have this kind of volume data set. I make a scan. I have this kind of cylinder here. It's a virtual drill core. And I can, of course, slice it, look into these kind of thin section here. We see bacterial mats from organisms that oxidize manganese and live on that. So they have a metabolism sensitive to something in the rock or in the water. And that was an interesting thing. So we see we have these cracks here, and so we could just see by microscopy without destroying the sample how life propagates in these kind of rocks due to these kind of cracks. That was a nice example. You have the 3D volume, you make virtual thin sections in any direction, and then you can characterize your process or look into it without destroying it. I have here some drill cores from basalt intruding into sediments. If a hot magma goes into sediments, it releases maybe gases. And it brings also very much heat. And if it intrudes in wet sediments, a lot of reactions are going on. And sometimes if you have carbonate in sediments where the volcanic material introduces, then you have a reaction, you form carbonate in the volcanic sill. And also sulfides that are present in the sediments interact by hydrothermal activity with these kind of basaltic intrusion. And that means it can be a sink for carbon. All these kind of intrusions in the seafloor of basaltic magma can actually be a sink of carbon, which is actually thought of potential locations for CO2 sequestration. You can think about it what you want, but of course that's what we can do. We can see what is the reaction, the process going on when you have these interactions and you fix the carbon in the rock. How does it go? You see some different things. We see here, this is the volume reconstruction of come on. No, does not go. Of this drill core. And we can also have this kind of shadow-based volume reconstruction, or we can make it more transparent, showing only the densest phases. And then we see, oh, we have got a lot of carbonate here, and we have iron sulfide. So all these processes taking up carbon, taking up sulfur, they have some kind of textures that we can think of the processes. And that helps us a lot. So we do the analysis, we do inspection with this kind of volume representation here, and then we can think of the processes again. Or if we have, for example, I can also use micro-CT if I do experiments in the lab, like some crack in the concrete, and you want to see if you have self-healing concrete, you pour water into it, some things in the composition of this cement, the Portland component, they can act really as a self-healing issue in this process of water flows through cracks in concrete, and that was what I was investigating with colleagues from Hamburg University. And so there are several theories. How does the self-healing process of the concrete is really happening in the sample? And so they made experiments. They measured in the lab the water throughput, and then they see it ceased. And that was the interesting thing. What of these theories was actually true? So of course they investigated with SEM and stuff like that. And then from this big block we took from several heights, we took several samples, and then we decided which one of those to scan. And at least these are very small samples here, but it shows something very important, that it's very locally you have the growth of calcite or carbonate or magnesium silicate in other places. So even if you have this bulk situation where you have a reduction of the flow, sometimes it's very, the precipitation as a reaction of the self-healing component is sometimes very locally, and we could focus it in comparison of different materials, different kinds of cements, so we saw different ways of closure of these things. That was quite nice, and then of course the colleagues did some reactive transport modeling to see how we can theoretically come across that. What we see, we have this kind of measurement of the local X-ray absorption. We have a point-focused X-ray source, a kind of magnetic lens system that focuses the electrons in the beam. They're hitting a diamond window, and the tungsten layer and the diamond window, and that is our X-ray source. It radiates all over the place in the cabin, and only where you have the detector, you have this imaging path for our 3D imaging. So here is a really optical magnification. If you have a large sample, and you want to image it as a whole, you have to put it very close to the detector. You cannot magnify it much, otherwise it would be out of the field of view. But if you have a smaller sample, like a foraminifera or some other component from technical stuff, you can put it very close to the X-rays, and if it's very close to the X-rays, it has a high magnification. So that's the thing. Small samples can be highly magnified. Large samples, not so much. But of course, if you have this kind of large sample, you could move it over here and then partially make a zoom, a high resolution scan only of a part of this interior. So that's also a good thing. You can first make an overview scan and then move it closer. And then you make, in the overview scan, you can look in the region where to focus your next zoom high resolution scan. So we see here different materials, and that's the thing. What we can do, we quantify the intensity loss of the X-rays passing the sample. So the original beam, the longer with the increasing sample thickness, and that the intensity of the beam is reduced because of the absorption of different particles. And this kind of absorption is mostly related to the mass extinction coefficient, and that depends on the X-ray wavelength. Okay, it's always the same, but if we have material contrasts, of course, in the same scan, it depends on the atomic number and bulk electron density. So it's a kind of density. Which kind of elements do you have in the sample? Heavy or light, iron, or maybe silica or aluminium. And that gives you a bulk electron density which is responsive for the absorption. So you can have a kind of material characterization, but you don't do elemental analysis. You do density characterization. And the best thing is density contrast that you want to have. So the materials, they have to be kind of X-ray transparent, which is really good for biological materials. Also good for ceramics, no problem. The fiber composites also very nicely. You can also have rocks and dense rocks. Some interesting feature are metals. If you have thick foils or something, they really strongly reduce the beam intensity and make the sample somehow not transparent for X-rays. So if you have iron samples or something like that, it's always good to make a test. So no problem if you have a sample you're not sure. Of course, come to me, approach me, and then we can make a test, scan, or we can think of how to solve your problem. Because in most cases, there will be a solution for it. Yeah, we have different detector systems. So if you look inside the device, we have an X-ray source. Here we have a detector system. So the point focus X-ray source makes this beam path to the detector. We have a flat panel that allows us to scan very large objects, from hand-sized up to hand size, but of course we can also make a magnification. But here you see we have several other cameras, and these are called X-ray objectives. So they are very small. Some are like this, my fingernail, and this is a detector 2000 times 2000 pixel. So we can have really high magnification. Something very small here, 1 or 2 millimeter, can be highly magnified, and we reach resolutions below 1 micron. And that's good that we combine those, because when you make a high resolution scan with maybe not so much, maybe only very 500 microns or so as a sample diameter, you don't see anything. So first, what you do, that's a very good thing. First, you do an overview scan. You have a big sample, and then you can go through this overview scan and locate an area of interest that you want to perform a high resolution scan. And then we can go in the software and set properly the center point of the spinning for the high resolution scan. So that's a very nice thing, that we can make first an overview scan, and then can look into the actual image of the overview scan, where is the most interesting part for you to analyze with a high resolution scan. So I think maybe it's a good idea, because to show you what you can do with X-ray microscopy, when I tell you something that I did. For me, as a scientist, it's maybe the same for you. Microscopy is part of the imaging toolbox. So I do a lot of other things. I have a rock sample from maybe a submarine volcano. I have here some particles of volcanic ash from a depth of several thousand meters. And in that particles, I see something like we have magmatic minerals enclosed in the glass, and they are dissolved sometimes, and here in some cracks we have the growth of some iron sulfides. That is the process I'm interested. So first I go to the SEM like you would do. You have an experiment or something, you go in the SEM, you see, okay, the glass is untouched, but the olivine is highly dissolved. So how does that happen? What's going on? Of course, we want to know what kind of sulfide is it. Iron sulfide, which kind of type? Is it pyrite or marcasite? So what I could do, first I make a thin section, I go to the microprobe, I see the compositions of the olivine. It's a magmatic material that contains magnesium, silica, and iron. So that's what I want to know, and the composition of the glass I can also have. And maybe if I want to see what kind of iron sulfide is it, I look into these kind of Raman spectra or FTIR spectra and see if I can decide which kind of mineral it is. And then I want to get some information about this process understanding. Where is the iron source of these kind of iron sulfide forming in these voids that the dissolving olivine has left? And of course, I want to see, why does iron sulfide always grow in the middle of these kind of dissolving crystals? These are my questions. So I make a scan of a particle, a very high resolution scan. The particle is only 1.4 millimeters high. And we see here's a crack, here's volcanic glass. Here we have a bit of olivine that is dissolving, and then right in his middle, there's this kind of layer of iron sulfide. We also see we have some spinels here, enclosed in the olivine. And that's really difficult to decide what happened here, but you also see a spinel right here in this layer. So I decided to make a high resolution scan, which we also see later. But what can we do now? First we can address the first question, where does the iron come from? If olivine dissolves and contains some iron, is it enough iron for this iron sulfide precipitation? So what I did, I measured the volume of the whole dissolved olivine. That means I measured the pore space, 3D model, and added, of course, the volume of the newly precipitated iron sulfide, because once the olivine is gone, this porosity and newly precipitated iron sulfide, that is the same amount of olivine that has lost. So I have the volume of the olivine, and then I know how much iron does it contain. I make a calculation, how much mole does this volume of dissolved olivine contain. And then I calculate if this amount of iron gets into the precipitation of iron sulfide, how much volume would that take? And so I can make a comparison. And I see if I take all the iron in the olivine, precipitated as iron sulfide, it is about 20%. And then I compare this with what I measure, and we see very good. It's really, I have a grip on the reaction that's happening. So all the iron was immobile in the rock, even due to the hydrothermal action, and it stayed there and precipitated with the sulfide. So I did it by measuring the volume of 3D models. The volume of this void and the volume of this precipitation. And then I saw something from this high resolution scan. How does it work? Why is it always in the middle, this kind of thing? And I saw here, if we have this crack, this is the dissolving olivine. Here we have newly formed sulfides. Sometimes, oops, I see here, there's a spinel grain in the middle. Spinel grains, we remember, are included in the olivine when he was growing in the magma chamber. And here we see something very important for the process. We see a heterogeneous nucleation of iron sulfide in the olivine. So the olivine is dissolving, and the structures in terms of nucleation of iron sulfide and the spinel are so similar that iron sulfide can nucleate on this spinel structure and forming crystals. And once a crystal is formed, then it, of course, grows different layers. And so that's what's happening. All these cracks, all these iron sulfides nucleates spinel, and that's the interesting thing of the process. Why are always these kind of sulfides in the middle of these cracks? It's because we have enter of water. When we have the magma pouring out the glass and the olivine, it cools very rapidly. So we have a cooling process. The olivine shrinks, but the spinel puts stress in its crystal lattice, and so there's a crack. And if we have cracks that end in glass, nothing will happen. But if we have cracks that end in this kind of voids, water can go through. And then we have this kind of precipitation alongside a crack. And of course, always these sulfides are in the center of the crack. And this is something that's very nice, because we gain a process understanding. If we look at these kind of scans that can not tell any other method I used, because we have the 3D idea of the substance, we can make volume calculations that I cannot do by SEM imaging or something else. So that is really an interesting process that maybe can also give you something to think in your environments, in your samples, what you could do with it. Yeah, we have a very interesting X-ray microscope. We have many special advanced imaging techniques. Phase contrast is maybe interesting also for the biological samples, because even X-rays, they have a birefringence, and then if you have something like you have in a very light substance, the material contrasts are not so good. So you can make this more visible by using this kind of special technique where you use the birefringence in the sample to get better grain boundaries or parts boundaries. I can show you that in the lab. We have a poster on that. I will not show you it here, but we have different kind of special things. One very special thing is the Debit mechanical test stage. This is something where you can put a sample here, and you can make compression, you can make tension experiments, or indentation like it is mounted here. You can put something very flat in it and then bend it, and then you can see the imaging, what is the unloaded state, what is the loaded state, and then you can do an overlay and you see some difference in mechanical reaction of that. And you can quantify that, of course. That's, for example, I did with some customers from the European Space Association. So they had some metal parts that were interesting for vehicles for space, some interesting alloys, and we want to see if you stress them by tension, how do they break? They had different alloys and they broke differently. I just show you what we can do in this cell. Here's this kind of mounting experimental cell, the Debit stage. It is in the beam path, and we just see a specially tailored piece. And if we pull it now, you see if we pull it, we have a bit force to pull it, then it's lengthening, and it always shrinks here. If we pull even more, then it breaks. And this kind of breakage is very rough, and they have different alloys that break really differently. So that was kind of interesting for those guys because they want to characterize the stability of their alloys in terms of mechanical stress. And this is what you can do also with this kind of special mounting technique. We can place your samples in the beam, make some mechanical testing, and then you compare the stages of these kind of experiments. Yeah, so basically you can now become a customer of this lab. And if you do so, there are two possibilities. You can measure yourself. If you have a lot of samples, it's really good maybe to get a teaching course, a basic training course, which is mandatory, and then you can use this device on your own. The colleagues from the Bremen Hochschule, for example, they are coming often and do a lot of measuring, so they know how to do it, and they can use this X-ray 3D microscope in application operation. Or if you say, I don't want to bother with all this technique, you give me the samples, you contact me, we have a chat, and then I do a service operation, which is also very handy, and then you get these kind of image volumes which you can inspect with several programs. I'm not sure if our time is up, but what we can do, that's the normal process, because I know the device, I know what it's capable of, and if you have a sample, the first thing we do is we just have a chat that is maybe an hour or 50 minutes or something like that, that we see what is the size of your object, but what is also the size of the feature of interest. Then we can think about what's the preparation that you have to do for me to get it imaged as best as we can. Imagine here we have a cylinder with a 30 micron thick layer of interest, some kind of coated layer on the tip. If you want to image the whole stick, 2 millimeters, and we have a detector field of 1000 times 1000 pixels, we only have a resolution of 2 micron. So nothing much, we have only 15 voxels to see in this kind of what's happening in the layer. If we zoom in, we make a magnification, great, we can have the image, the layer, maybe with 60 or more voxels, but then we only have a part of the sample. That means if we have a layer of 120 voxels, a voxel size not of 2 micron but of 0.25, we have an image field of view of 250 micron, but from the 2 millimeter, 1.8 millimeter of the sample is not imaged. So this is not good. We lose a lot of intensity, we lose a lot of contrast, and this is something we have to talk about. Then we can perform the scan, and then you get your data, which you can download from our servers. I think the time, no, I have still 5 minutes because we started 20. But this is something, yeah, you can see, keep your samples as small as possible. Like in this example with the 2 millimeter, if we scan the whole thing, we don't see anything of this. We image the whole stick of 2 millimeters, but we don't see anything in the layer. if we make a high resolution, we see something happening in the layer. But our sample has to be cut. It's not like this. It's about 400 micron thick. So it's really preparation work. If you have this kind of alloy something, you have to prepare it, because otherwise this is not imaged. If it would be 2 millimeter, it's out of the image. But if we want to have a good image from this layer, we have to cut our sample. That's always an interesting thing, because when you have a sample and you cut it, maybe you impose some destruction on it. So it's always a tricky thing to do. But there are several techniques that can help us. Like we say, we can use also micro-CT in relation to other techniques. For example, if we have this kind of TM or FIB-SEM or something, it's always a different field of view in relation to the resolution. And here we have something microscopic characterization of compound layers, what we did with Frau Sommer from the IWT. So she could do some SEM imaging, and I imaged her samples in a different, in a broader context to see these kind of nitrided layers here. What are their inner structure? That's way beyond something you can see with the SEM, but it gives you some ideas of the processes that happen, which you can maybe not see when you're looking at this kind of scales. So, yeah, maybe you include the thing about the techniques you have, and maybe if there's micro-CT always brings a different view to it. So if you want to integrate 3D imaging into your research, of course, a part of it is the computer-based image processing. And there are good programs, free of use. And the first thing I encourage you to do, if you would like to look at your samples for yourself, to use Fiji. We have several quantitative image analysis software to inspect these data sets. Fiji is a very nice thing. It can work on PCs or on Macs. And I can provide a script with short instructions. And what you can do, you can really have this kind of virtual drill core, your sample, and you can scroll through it. You see, here's a slider, you can load all the image, you can scroll through it, and then you have some first ideas. And this was actually what I was doing years ago when I was a bit younger. So we used to inspect some kind of micro borings from worms and whale bones. In the old days, it was really a nice thing when I was in Kiel. And the TV, local television came because it was a great thing, and we published it in several papers that were interesting. What I want to tell you, these kind of things is very easy, and I did it with a software like Fiji. So that's not, it's not difficult. So also, if you have material science here, ancient pottery, of course, we have kind of temper, we have clay matrix, you can use several things. All this imaging Fiji is capable of doing. You don't need an expensive program. Or you could look at it if you have porosity, like if a clay has some roots components or needles, you can do archaeobiology, biology in your samples, and that's quite nice because micro-CT, of course, the pore space is also a phase, and you can make a 3D model of the pore space of something that is burned away during the process of burning the potsherd. But still, you have some prehistoric vessel, and you see in the walls, you see something about what plants were growing or what were they eating. Because sometimes the labs were not so clean in the ancient days, and so always some stuff ended up there. And this actually I did with Fiji, looking into processes. How did they form their vessels? You have a coil, you have some techniques to make it smooth, and you see it, different techniques for different ways of porosity. So you see here, you could do that with Fiji. I was really coloring two models with Fiji. Porosity here, and you can make a 3D model of the porosity and use Fiji, a very simple program, to get these kind of results. Of course, nowadays you can also have other programs. For example, an interactive learning and segmentation toolkit, Elastic. It's a very nice program, free to use. No machine learning experience required, but it does a really good job. It's also working on PC and Mac. And if you have something, you could samples here, maybe some cells and some other stuff. You could give some scribblings, and then later this recognizes the stuff in your image. And it works quite well. I did it with several minerals, with silicates that are very similar. So it really works. Cool stuff. And also a more complex imaging suite here is the ORS Systems Dragonfly, and that's a kind of cool thing because if you can apply for a scientific license, and then it's free of use. It's a huge and very capable software. You can use it on your local PC, or we will soon have an installation on a server available from the MicroCT lab in cooperation with Oliver Plumper from the Geoscience, because we applied for some server cluster. And this is where we install this kind of program. And once it works, that we can access this cluster from the outside, not only from inside Marum, it will be available also for our customers. Yeah, with that, I want to thank you very much for your attention. I hope I can have shown you that this kind of 3D microscope is creating images that you can inspect and that help you to get an idea about processes or about phases. And in case you want to contact me, please feel free to do so. Thank you very much for your attention.